Okay, this section we will talk about the inverter circuit. This is a typical inverter, the low voltage drive. And here is AC to DC. It's not shown here. So if it's AC to DC. And here is the DC. And this is the inverter. Like for three-phase, two-level inverter, we have a 6 IGBT. And for each phase, like U phase, we have up IGBT, high IGBT, and lower IGBT. And for each IGBT, there is we call the diode, free wheel diode in parallel, reverse parallel with IGBT. And this is a U phase, V phase, and W phase. And actually, when this IGBT is on, this IGBT is off, then this point the output voltage is high level, high plus, we call the plus DC. Actually, depending on the direction of the current, if the current go this way, and then this one is on, will be go like this. Otherwise, if current is on the reverse direction, then will be go through this diode and then to the positive DC bus. But both of them, you can get the plus DC bus on the output point voltage level. And also, when those two is off, those IGBT is off, this IGBT is on, you get a negative DC. So either this one on, off, or this one off, this on. You cannot get those two IGBT turn on at the same time. Otherwise, you get a short circuit, and you will have fire. So because there is we call the delay on the IGBT firing, either on or off. So for safety issues, we will set a time we call the dead time, dead zone. In this period of time, both this one and this one, both of them are off for safety issues. So during the dead zone, the output voltage is decided by the current. If current goes this way, then this diode goes through this diode, and we get the negative voltage. If current goes this way and goes through this diode, we get the positive voltage. And here's the Pwm principle. For example, this is the sinusoidal, half cycle of sinusoidal. And at the different point, you have different value of the voltage. But for the inverter, because we convert the AC to DC, the DC voltage is fixed. So how can we get identical AC voltage with a fixed DC voltage? Then here comes the Pwm principle. That means although the value of the DC is fixed, but the width of the pulse can be adjusted. For example, like on the peak of if we want to get the peak voltage on the output, then in this type we will have the very wide pulse, the highest in width for the pulse. And then for the low voltage we have the very narrow pulse. So actually the area of each pulse is corresponding to the value of the demand AC voltage. So this is called the Pwm. Here we can see, the waveform here is the reference, like the sinusoidal waveform. And this one we call the carrier wave, Pwm signal. And we can do the Pwm by compare the reference with the carrier wave. If the reference is higher than the carrier wave, then we get the positive voltage. Otherwise, we get the negative voltage. So by this kind of modulation, we will have the voltage waveform like this. The voltage is fixed DC voltage, but the width is different. So by this kind of modulator, you will get identical voltage, sinusoidal identical voltage. The square, the area of the pulse, representing the value of the waveform. Now here is a typical three-phase modulation. Here is the carrier wave, and U phase, V phase, W phase, 3-phase. And for each phase, we compare the reference with the carrier wave, we get voltage, U phase, V phase, W phase. And if U phase minus V phase, we get line-to-line voltage, UV. If we look at this voltage, it's a fixed value, but because of the change of the width of the waveform, we can get identical effect of the sinusoidal like this. Okay. So one thing I want to mention is all those voltage, line voltage, U, V prime. V is pointed here, and the prime, the reference point here is the neutral point of the DC, not this one. This is the motor. So N is the neutral point of the motor. N prime is the neutral point of the common DC bus. So those 2 points, the voltage is different. The voltage between those 2 points we call the common mode voltage. It's not zero. That is a waveform with a high frequency. So if we look at the real motor voltage, motor phase voltage, U to N, the waveform is different from U to N prime, because of the common mode voltage. So this waveform is different. And this is the output voltage and the current of the inverter, 2-level inverter. This is Pwm voltage, and the current is very close to the sinusoidal. So here's 2 issues. One is the carrier wave frequency. Like for the carrier wave frequency for the low drive is typically kilohertz, for example, 2 kilohertz to 10 kilohertz, for example. So although, if we look at the output voltage, you have certain level of voltage THD, especially on the high frequency like this level, kilohertz level. But for the motor current, because the reactor of the motor, the impedance of the reactor is proportional to frequency. So that means for the high frequency voltage factor, because of the high impedance, so the high frequency current is very low. That means you have a high value of voltage for the high frequency, but very, very low current, high frequency ripple current factor. So the actual current waveform is very, very good. The current THD is normally lower than the voltage THD because of the effect of the impedance. Okay, that's all for today's section. You can scan the code to get more information. Thank you.